already done?
Yeah. Okay, welcome back to the advanced course. So remember I was talking about singular value decomposition and blah and other stuff like that. Okay, so now we're actually going to dive into what the hell is singular value decomposition. Right, so remember, so do you all guys, as I'm assuming all guys here in the advanced at least understand what matrices, right? Yes? No? Yes? Okay, right, just to clear up some things, I'm going to name the matrix as X, right? So the matrix I'm going to name it is X, okay? So what is a matrix? Well, it's just a table of numbers, right? Like 1, 2, 3, 4, 10, 20, I don't know, 30, 40, right? This is like a matrix, right? It's just a table of numbers. If you put it into a table, right, this is just a table. It's just you delete in the matrix formation, in the matrix notation, you just delete all these lines. So that's just a matrix, okay? So I'm going to denote X as the matrix now, okay? So, it's horrible. Whatever. Okay, and remember, the theory of singular value decomposition is any single matrix can be decomposed into its components, U, sigma, sometimes people call it D, and V transpose. Okay, so what is U? Okay, what is U? U and V are both orthogonal, right? So what orthogonal means is if you do U times by U transpose, it's the identity matrix, right? If you do U transpose times U, so the other way around, it's also the identity matrix, right? Just different size. So what's the identity matrix? It's just 1, 1, 1, 1, 1, 1, 1, 1, like one's all on the diagonal, zeros everywhere else, right? That's the identity matrix, right? Do you guys get that? Whatever. So U is orthogonal. So what it means is this property holds, right? V is also orthogonal. So V's property, V transpose times V is also identity, right? And V times V transpose is also identity, right? So all these things hold. Sigma, or D for diagonal, is a diagonal matrix. So just like identity, the only difference is the numbers are not 1 in the diagonal. It's like 2, 3, 4, I don't know, root 5, 10, la la la. Everywhere else is 0. Right, so that's sigma. It's just an identity matrix, just the numbers are not all 1, they're like other numbers. 2, 3, 4, whatever. Okay, I don't know. But these are all numbers. Right, and so what this means is that any single matrix can be decomposed into 3 components, 2 orthogonal and 1 diagonal. Right, so okay, so the difference is so what is the difference between U and V? Right, U is a column vector. Or column matrix rather, right? Columns, they're columns, right? Sigma is a diagonal matrix, everywhere else is zeros, right? And V transpose, remember it's transpose. Do you guys know what transpose is? Transpose is like, if you have some sort of matrix like this, 3, right? The transpose is just, you swap the rows and columns around, so 2, 3, 1, 2, 3, 3, 4, 5, right? Like this. The transpose of just a 1 is just a 1. Right? And the transpose of 1, 2 is just 1, 2. Right? It looks like that. So that means that the vectors, the columns, get translated to rows. Right? So V transpose is just rows. Right? So that's what it looks like. So what does this actually mean? Right? It's actually a rotation followed by stretching followed by a rotation. So just pretend if you have like some sort of large data set, 10 million columns, how do you actually rotate the whole 10 million columns, right? So if you have 10 million dimensional space, you have to rotate something in 10 million dimensional space. That's what U does. It rotates something, like some way, right? Sigma, stretching. So what it means is stretching is, if you have a 10 million dimensional data set, you rotate it at first, you want to stretch it, right? Stretch or like make it skinnier. So that's what that does. And the V transpose is also rotation. So once you rotated this, okay, step 1, rotation, right? Step 2 is stretch. Step 3 is rotation again, like you can rotate back or rotate more. But that's what singular value decomposition is. It's just a component, it's just a combination of rotation, one is rotation, the second one is stretching, and the third one is rotation again. Right? So rotation, right, stretching and rotation. Yeah, do people get that? Do you know what a rotation is? Kind of? So pretend if I have this whiteboard marker thing, whiteboard eraser thing, right? Rotation just means like literally rotation. Right? If you plot all of these numbers onto like a matrix, if you rotate it, the matrix should rotate in the correct way. Stretching just means you want to make this eraser larger or skinnier, right? That's what stretching does. And rotation again just means after when you make this smaller or thinner, then you want to rotate again. Yeah, do you guys get that? Kind of? No? Yes? Yep.
What's the point in like rotating it and like everything else?
What's the point? Okay.
Yeah.
Well, what it means is that any single table of values is a combination of rotations and stretching.
Yeah.
So any single. So what's the point?
Yeah.
I will show you.
Okay.
Okay.
And VT should be the row matrix, right?
Sorry.
U is column matrix and VT should be row matrix.
Correct. So U is columns, V is rows. That's right. I'll show you what's up. Yep.
And one more question.
Yep.
So if I have some dimensions of X matrix, like
Yep.
M into N,
Yes.
then so what would be the dimensions of the three components? I think that would make more sense.
Okay. That's a good question. Well, let's try to infer it. Okay. So point one. Let's say that we have a I don't know 50 column data set with 1,000 rows. Right. Let's just do that. Right. Remember, first step is diagonal. Right. The middle one has to be diagonal. So what do you think the middle one is going to be? Oh, actually, I think I'll write it in a better way. So U is here, times by sigma is equal to U times sigma, right? And V transpose is here, times that is U V transpose, right? So remember, so remember, the first one is this one. Oh, no, I'll do X. Right, this is exactly equal to X, right? This is exactly the same as X. What this means is that the last one must have columns 50 and 1,000 rows, right? So what does that mean? That means U sigma must have 1,000 rows. And that means U must have 1,000 rows, right? If you apply it, like this is just, yeah, do you get that? If this one has to have 1,000 rows, this one must have 1,000 rows, this one has 1,000 rows. Because if you do matrix multiplication, the rows have to always be equal to the same, yeah? No?
Columns, I think.
Okay, let's do columns.
Row and columns should be the same.
Well, let's see. So, okay, by induction, well, not really induction. Okay, step one. So if this one has 1,000 rows, that means that these ones must have 1,000 rows, right? Yes? No? Yes? No?
Yes.
If you, right, look, if you have 3 rows, if you do matrix multiplication, 1, 2, 2, 2, right, what's the final result? It has to have 3 rows, right? If you do this times that, it has to have 3 rows. So what it means is this one must have 1,000 rows, because the original one is 1,000. Yeah? Do you get, but remember, this one's diagonal, right? So how many columns does the diagonal matrix have?
1,000 by 1,000
Same. Should be same.
So 1,000.
by 1,000.
And then you can deduce everything else, right, using the same logic. Although it's not, well, I mean, I don't know if the,
I think it should be 50, not 1,000.
or did I do it wrong?
Because like when we are multiplying, so what?
Oh, no, but then this is 50. This is 1,000. Because you reduce the columns. You can reduce columns, you can't reduce.
Then we can't multiply, that's what I'm saying. Because for multiplication, rows and columns should be equal, right? Not the rows. So it should be 50, like middle one.
Huh? Did I do it wrong? No, wait, what? No, wait. No, this one has 1,000 rows, right? So 1,000 rows times 1,000 columns is, oh.
Yes.
My bad. You're right, it's 50.
Yeah, it's 50.
Okay, sorry. Yeah, and so on. You just change everything up then. My god, sorry then. Okay, well, we don't need to talk about that then, but you're right, my bad. Okay, anyways. So do you guys understand like singular value decomposition is a rotation, right? A rotation followed by stretching, followed by another rotation, right? Yes, do you get that kind of? Oh yeah, you had a question.
Yeah, why can't you just rotate once and then scale?
Oh.
Is that because we're not dealing with square matrices?
Interesting question.
Why do you
So
have to do it twice? Because you feel like the scaling wouldn't change.
okay, so firstly you have to do a rotation, right? And then you have to, oh, yeah, that's right. Actually, it's because it's not square. So you can't actually do a rotation on a non-square matrix. So you have to translate it to a square matrix first. And that's why you have to do the rotation first, because it's not square. So if it's a non-square matrix, you have to do a rotation, then a stretching, then a rotation, which is the same as rotation and stretching, which is also the same as stretching then rotation, right? Because if you do a rotation and then you stretch it and then you rotate it, what's the difference? Because a rotation, you could just revert back to rotation, right? But yeah, it's because the original matrix is not square, and that's why you have to do this. It's kind of like a trick kind of thing. Yeah, kind of answer your question. Anyways, so the key point is U and V are orthogonal, right? So U times U transpose is the same, is identity, right? And V times V transpose is also identity. Okay, that's the key takeaway. Okay, now, what is X transpose? What do you think X transpose is? Like this transpose. What's that transpose? So, remember, if you transpose a multiplication of matrices, you have to revert the order, right? So it's not, X transpose is not U transpose times sigma transpose times, okay, the transpose of a transpose is original back, right? So it's not that, right? In fact, you have to revert the order of things. You have to put the V first, then the sigma transpose, then the U transpose, right? You have to revert the order. Just the point, right? If you don't revert the order, the transpose won't work, so you have to revert the order. Okay, so that's X transpose. So now my question is, what's X transpose times by X? X transpose times X is V sigma transpose U transpose times by this, U transpose sigma V transpose. Right, but remember, what's U transpose U?
Identity.
Yeah, identity, so delete this. Right, we don't need that. Identity is just 1. So the answer is this. X transpose X, I think I wrote that right. Yeah, it is V sigma transpose sigma V transpose. Yeah, do you guys get that? Okay, another way. What happens if we do it the other way around? What is X transpose? X times X transpose. Right, so X is U sigma V transpose. X transpose is V sigma U transpose. Remember, what's V transpose V? The identity. So the answer is U sigma right? U sigma transpose U transpose. I think that's right. Is that right? I remember to correct my mistakes. But yeah. So okay. So now the question is, why the hell am I doing that? Well, do you guys know eigenvalue decomposition and eigenvalues and eigenvectors? Do you remember this formula? X can be decomposed into V lambda V inverse? No? Or V lambda V transpose? Whatever, I'll just tell you what it is. Okay, so do you know what an eigenvalue and eigenvectors are? Okay, so pretend I have some sort of matrix, some sort of high dimensional data, like 10 million dimensional, right? But sometimes, like if I do some manipulation to the data, like rotation or whatever, or stretching, right? Most likely there is some sort of plane or some sort of vector in between it, some sort of like basis vector, which when you stretch it, it will just increase by a factor. Like if I have like this is the plane, right? If I stretch everything, my hand will just stretch like by a multiple, right? It won't, like if I have this pen, if I stretch this pen, right? These ways, it's just a multiple of the original, right? If this length was 10, and I stretch it by a factor of 2, what's the new length? 20, right? but this side is probably stretched by 5, and this side is stretched by 5. So the eigenvalue is the number that I stretch by, right, which is 5. And the eigenvector is just the actual pen's coordinates, which is the, so the eigenvector is the plane or the area, like the I don't know how to explain it, like if it was like 10 million dimensions, like some sort of like plane or.
Is it like the sample space of possible values? Like one way of explaining?
Sample space of all possible values.
Yeah.
The eigenvalues and eigenvectors.
Yeah, that's one way of describing.
Oh yeah, actually that actually kind of makes sense because yeah, it's like the original thing which you can generate everything out of. Yeah, so it's like it's the minimum vector in the space which you're allowed to, like when you manipulate all the vectors, this one, the only one vector in, well there's not one, there's like multiple, but these vectors, if you manipulate the whole table, these ones will only increase by like factors of stretching, right? If I increase a factor of 10, the eigenvalue will be, I don't know, 10 or 5, I don't know, it depends. Depends on the situation. And this is the eigenvector. Yes, kind of?
I'm gonna try and show.
Oh yeah, you should show, yeah.
FYI, if you guys want to learn maths, I really recommend the YouTube channel called 3 Blue 1 Brown. Like they have some really good visual representations of what's going on. Like I watched the.
No,
I'll
right,
show you.
yeah, I watched them as well. Yeah, you should show them now. Oh, well the thing is, oh yeah, the screen's over there.
Is it on? Tell me when it's on.
Yeah, it's on.
It's on. Alright.
Yeah, I think, well.
I hat is one such special vector. The span of I hat is the x-axis, and from the first column of the matrix, we can see that I hat moves over to 3 times itself, still on that x-axis.
So that's what Daniel's talking about. When you move the entire space, that vector just shifted length. Whereas you see the other vector, this one.
The basis vector I hat is one such.
The vertical one actually shifted its angle when the whole space moved, but the horizontal one just changed its length. So that horizontal one is an eigenvector. And there's also another eigenvector with this specific transformation, which hopefully they'll show. Yeah. So that yellow vector also just shifts in length. It doesn't change directions. And because of that, it's also an eigenvector. So hopefully that made more sense to everyone.
Yeah, kind of.
So with each kind of, you can think of a matrix as a transformation of the space. So kind of, in this case, it's kind of stretching and rotating a bit. So with each kind of transformation, there are certain eigenvectors and eigenvalues. So they're associated with the actual transformation of the space.
Which YouTube channel was it?
Sorry?
Which YouTube channel is it?
Which?
3 blue, 1 brown.
3 blue, 1 brown. Yeah.
3 blue, 1 brown. Yeah, do you kind of get that? No? So like if, yeah, so it's the vector or the line or the plane, which whenever you do some sort of transformation, like you rotate the matrix, you stretch the matrix, you rotate or whatever, right? The change to that plane is just increase or decrease, increase or decrease. It's just stretching, right?
Well, not always.
Oh, okay.
So sometimes you can just have a plane that just rotates along itself, in which case there's no eigenvalue or eigenvector, because any vector would have to rotate with it.
Yeah. Okay, yeah. Should I continue? Anyways, okay. So remember, x transpose x is v times the diagonal matrix transpose times the diagonal matrix times v transpose, and this one, right? U da da da. Right. So now, okay, eigenvalues. So we discussed about what is an eigenvalue and what is an eigenvector. So the question is, how do we actually find these vectors in some sort of matrix? Right? If you have a 10 million dimensional space, how do you actually find these vectors which have the special property that if you rotate the matrix, this vector will just stretch or whatever, right? Something like that. So the way to find it is eigenvalue decomposition. Is x, so remember that x means the matrix, is equal to, right, the eigenvectors times the diagonal matrix of all eigenvalues. Remember the eigenvalues is, if I stretch the eigenvector by like 10, the eigenvalue is, I don't know, 5. I don't know, I'm just making stuff up. Because you stretch both sides by 5, so the eigenvalue is kind of 5. So that's lambda, the capital lambda, is a diagonal matrix of all eigenvalues, like 5, 4, I don't know, 0, everything else. Right? This looks suspiciously similar to sigma. Right? Sigma is also a matrix with numbers. Right? Not ones, numbers. Right? This looks suspiciously similar. Right? And the V times lambda times V transpose, or V inverse. But don't worry about that. I'm just saying V transpose for now. What this means is that the eigenvalue times this stretching times the eigenvalue. Right? So if you have some sort of eigenvalue, you stretch it and you times it again, it should go back to the original matrix. This is just eigenvalue decomposition. You don't actually need to know what this is about, but I'm just telling you, we just need to use it for now. Eigen decomposition. Okay, just remember this formula. You can search it up later. But, okay. Can anyone tell me what's the similarities between this and that? The top one and the bottom one. Oh, okay, fine. Let's just do that one. X transpose X is equal to V sigma transpose sigma times V transpose. What's the difference? What's the similarity? And what's the differences?
So the sigma transpose sigma should be equal to that lambda.
Yeah. So in fact, sigma, remember, what's sigma? It's that, right? The diagonals are numbers, everywhere else is 0. So what's sigma transpose? What does sigma transpose look like? Same thing. So what's sigma transpose times by sigma?
Square.
Correct. It's just the square of the sigma, so 25, and so on. Right? So in fact, this is exactly equal to the eigenvalues, and this is exactly equal to the eigenvectors. So what this means is that X transpose X is just an eigen decomposition, right, on this, right? You decompose these eigenvalues, you get this, right? That's all you, yeah? So so remember if you do it, this is the normal eigenvalue decomposition of all matrices. Not all matrices can be decomposed though. You have to use some techniques, but once you decompose it, this is exactly equal. Yeah? No, yes, no, yeah?
Then it means X transpose X is equal to X as well, if they are equal.
Sorry?
That means X transpose X and X are equal if they are equal.
Oh. Yeah, if that, well, I mean, I just use this notation for, well, it could be, yeah, if they're equal, correct. But in most cases, no, it won't be equal. But I just use X as like probably it could be like B. But yeah, I'm kind of like confusing people. X and X is the same thing. I just mean X as any single matrix. And this X transpose X, it's just you times X by X transpose X. So anyway, it's like, okay, so if you use this logic, right, then how about this one? What is this? What's this X transpose? Does this look familiar? Right, remember the notation was X is equal to V, right, lambda times the V transpose, right? Isn't this the same as this as well? And these are just repeating, right? These are just notation, don't actually, I mean, I could have just chose Y is equal to the eigenvectors times by the lambda, right? Maybe this will make more sense. Right, this is the same layout, right? So in fact, what we can see is that singular value decomposition is just finding the eigenvalues and the eigenvectors of that X transpose X and X transpose. Right, okay, maybe you're thinking like, what the hell is the whole point of this? I will show you now. Do you guys know the linear regression formula? Remember I said something times weight plus something times height plus something times age is equal to happiness, right? Right, yeah? These numbers, like 5, 6, -3 something, right? These are just called, they're not actually meaning anything.
Variance.
Right, they're called, I'm just going to put this as the coefficients theta, right? Theta will be, right, theta is the coefficients, right? Theta is just a vector of 5, 6, and -3. You just put these numbers in some sort of vector, right? And what's x? X is just the matrix of w, height, and age, right? Weight, height, and age, right? That's x, right? So x times by theta is equal to happiness, right? I hope you get that part.
Put a line on the theta.
Oh,
No.
what line? What are you
Just to
talking
make
about?
it a vector.
Oh, okay, fine. Yeah, did you get that? Just matrix multiplication, right? The x times by that is equal to happiness, right?
No,
Weight
it's just an
times by.
intercept as well.
Oh, he cares about the intercept. You could just put a 1 here, right?
Yeah.
In the,
Well, that's what you did.
yeah, oh, yeah. So remember, so weight times by 5 plus height times by 6 plus age times by -3 is equal to happiness 1, right? Happiness 2 is equal to this times that plus this times that plus this times that. So this is actually correct, right? X theta is equal to happiness. So the question is, what is theta? Or how do we actually find theta? Well, if you remember you've probably seen this. Theta is equal to x transpose x inverse x transpose y. Right, this is y. No? Yes? No? Kind of the least square. Okay, but just look at. Okay, I'll just write it there. Okay, you don't actually need to know how I got that. I'll show you how we're gonna get that. Okay, the key takeaway from that equation is, look at this inverse problem. Right, there's an inverse, right? So, the question is, can all matrices be inverted? Yes, no? Right, so how do we invert this? What's the inverse of this? Well, I mean, normal maths, in the maths that we learn, it has to be square, right, at least, for you to invert it, at least square. And the determinant has to be not 0, right? So many matrices, your determinant will be 0. But like, pretend I'll give you an example. Can we invert this? No, because the columns are the same thing. You can't actually invert that. Well, I mean, you can try, but I'm sure you won't be able to invert that. Or maybe you can. I don't know. But most likely you're not allowed to invert this because the columns are exactly the same. And remember in the data, 1, 2, right, sometimes, remember I told you, sometimes the data is like correlated with each other. Because like, you know, in Lasso, we try to remove all the useless 90% of the data, only keep the 10%. Sometimes it can just be the double of your original vector. Maybe age is like, maybe weight is just the double of age, right? And if you have this problem, right, it's just the double. You can just decompose that to 1, 2, 1, 2, right? You just divide by 2. So this, you can't take the inverse. So the problem is, using this equation, you can't always take inverses. Right? That's the problem. You can't take inverses, which means you can't use linear regression until your system fails. Right? You will never actually get a model. However, with singular value decomposition, we fix this problem. Okay, now for some interesting stuff. Okay, remember, x transpose x is equal to v sigma transpose sigma times v transpose, right? So my question is, what is x transpose x inverse? Remember, the left-hand side, I can never always compute, right? X transpose x, just this left-hand side, I can't do anything, right? I can't do anything with it because sometimes you can't do the inverse. But remember, what's singular value decomposition's theory? What does the theory say? All matrices can be decomposed into its singular values and rotation and stretching, right? All matrices. So what this means is that all matrices should have technically an inverse. This should have an inverse. So what is this inverse? So it's V, sigma transpose sigma, V transpose, or inverse. Right, so how do we actually compute the inverse? Go back to eigenvalues and eigenvectors. Remember, eigenvalue is the matrix M is equal to the eigenvectors times the eigenvalues times the eigenvectors transpose. Right? So my question is, what is, using this eigenvalue decomposition, what is M theta? So what is the power? What is the power of matrices? How do we take the power of a matrix? Like, what's squared? Right? N squared is just M times M, right? But if you remember, it's actually just the eigenvectors times the eigenvalues squared times the eigenvalue. Yes, do you get that? Do you remember this? No? From your first year maths? No? This is first year maths, but so what it means is that if you square a matrix, right? You're doing a transformation of the original matrix. But what does eigenvectors and eigenvalues do? The eigenvectors and the eigenvalues are only stretching, right? Hence you just square it because you're just stretching it. And that's why everything else keeps the same. That's the whole point of eigenvalues and eigenvectors. Instead of timesing, so what happens, what's m to the power of 1,000? Right? What this means is you're getting a matrix and you times it on 1,000 times. This is just the eigenvectors times lambda to the power of 1,000. Right, so what this means is, I remember the eigenvectors is just 10, 20, 30, I don't know, right? You don't actually need to times the matrix m times by m times by m times by m times by la la la, right, all the way to 1,000, right? You don't need to do that. All you need to do is times. You just need to multiply. You just need to to the square to the power of 1,000 of these eigenvalues, and then you just times it on. This is just a maths technique thing. Yes, do you kind of get that? No. I mean, probably I didn't explain it right. I just want to continue on. But eigenvalues and eigenvectors allow you to take the powers without actually taking powers. You only need to get the eigenvalues. You just take the power of the eigenvalues, and then you're fine. So my question, so the problem is, so what's the difference between taking powers of this and taking powers of that? Remember, all of these have zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? If I take the power of this to square, it's just 100, 400, 900, and so on. Right? So it's actually computationally cheaper. Yeah, do you guys kind of get that? Okay, now I'm actually going to use that. So a trick. What's m inverse? What's the negative power? Isn't it just this? M inverse is just the eigenvectors times eigenvalues to the inverse of this. Isn't that correct? And what's the inverse of eigenvalues? It's just 1 divided by. Right? So that's just a trick. In fact, you can do -2 if you want. But I'm just going to do inverse of 1. The first order inverse.
What does -2 mean?
It doesn't mean anything.
Yeah.
There's no such thing. Well, it kind of just means inverse and just square it later on. Well, that's not the correct notation. That's not the correct notation, yeah. Anyways, just remember this, okay? The inverse is just the lambdas, 1 divided by all the eigenvalues, okay? Am I going a bit too fast? Or am I like skimming over like everything? Okay, but anyways, okay, what this means, how do we take the inverse? Isn't this just V? Isn't that just that? Isn't this exactly the same as this formula? Remember, sigma transpose sigma is just sigma squared, right? So this is just a diagonal matrix, which means you can just use this formula across. So doesn't this mean now we already have like, okay, so we have x transpose x inverse is just this, right? Yes, do you agree with me on that, using this formula? No, yes? Okay, the last step. What's x transpose x inverse times by x transpose? Well, it's v sigma inverse v transpose. So what's x transpose? V sigma transpose u transpose. Remember what's v transpose v? The identities, delete that. Right, now we have x transpose x inverse x transpose is equal to v sigma transpose sigma inverse sigma transpose u transpose. Okay? Now notation. If you have something transpose times by something, and you have an inverse, and you times it something transpose again, this is called a pseudo-inverse, or a dagger. Right? And a dagger is the pseudo-inverse. So what this means is the pseudo-inverse of x is equal to v, the pseudo-inverse of the sigmas, times u transpose. It's just, I just rewrite it in a cleaner form. Okay? So what this... Right, remember, look. Doesn't this look like that? Right, just sigma and x's. So that's why I put the sigma pseudo-inverse. Right, technically pseudo-inverse of x is just 1 divided by the thing. Right, and so what we have found is that the pseudo-inverse of x is just v times the pseudo-inverse of the sigmas times u transpose. right? Yeah? I mean, if you don't know what I actually did, I'll just write it here as the final. So x dagger, remember this is the dagger, right? Not positive, dagger for pseudo-inverse is a v sigma dagger, or for pseudo-inverse, U transpose. So what this means, so the whole point of this is you can't find the inverse of this sometimes, right? But remember, singular value decomposition says that all matrices you can find a decomposition. Well, we just use singular value decomposition's power, and we have found any inverse of any matrix. So if you have 1, 2, you should be able to times it by some sort of matrix. You get 1, 1, 0, 0. And that's the pseudo, yep.
So in your example before of age and weight not being unique variables, they
Yep.
are essentially matched 1 to 1, just one's slightly larger or twice as large.
Yes, correct.
If you're doing these pseudo inverses, what values are you placing in those parameters, given that
0.
they're both 0?
Well, okay, so what will happen is that the pseudo-inverse, okay, so yeah, good question. So if you use this, right, just the normal
You don't
inverse.
get a result, right?
Yeah, so, well, if you use the normal inverse, if you have matrix, like if you have the columns, not multiples of each other, like 2 times something, then if you use singular value decomposition, these sigmas should look like 1, 2, 3, 5, 10, root 10, I don't know, -1, -5, right, and so on, right? Let's just say that ends, right? But if you do in fact have 2 times something, or 3 times something, then these ones would just be 0, 0, 0, 0, 0, da, 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 1, 2, 3, 5, 10, and then everything else would be 0.
So both of them end up 0. So
No, one of them will end up as 0.
yeah, how does it decide? Is it just like the one that ends up at the
Well, it depends on how you implement your algorithm.
Okay.
It's either the first one or the second one. Well, normally it's the one that is the smallest, normally.
Okay.
But it depends on how you implement your algorithm. It will always keep 1 as the column. Like one of your columns as not the independent from the others. Yeah. Does that kind of answer your question?
Yeah, so I've done the lasso regression before, and I thought like it was the lambda that was causing them to go to 0, as well as the pseudo. But then it just
So this
does
is
the zeros
singular.
as
This
well.
is a bit different. Singular value decomposition. So what these numbers mean is it explains the variance of these vectors. So what it means is pretend your data. So that's the whole point of principal component analysis. Maybe your 10 million dimensional data set is just moving forward, right? So maybe I don't know how to visualize 10 dimensional data, but if you have 10 dimensional data, maybe there's some sort of line which fits through everything, right? So these numbers just indicate in which 10 dimensions is the most important. So like, is your data always going towards the first dimension, or the second dimension, or the third dimension, or the fourth dimension, and so on? Maybe it doesn't even go to the other dimensions, if you get what I mean. This is not, so lasso regression is a little bit different from singular value. But, no, yes, kind of?
I know, just my understanding of principal components analysis was that it wasn't just getting rid of, it was like forming combinations of other values. So I was just a bit confused
Well,
about what you're talking about.
singular value decomposition is technically principal component analysis. What these, remember what I said, what is this? What is that like intuitively? So remember what's a V and what's a U?
Their rotations.
Correct, rotations. But what's sigma?
It's a stretch.
So what does stretching mean? So if I have 10-dimensional data, and these numbers indicate stretching, right? If I stretch a data set by 10, by a factor of 10, in the 10th dimension, right? And in the second dimension, I only stretch by 1. Which one's more important?
10.
The 10th dimension, right? The 10th dimension has a stretching of factor of 10, right? And singular value decomposition captures these stretching factors. So like maybe the 1,000,000th dimension has a stretching factor of like 0. I don't know, right? There's no point of stretching it. But that's what singular value decomposition does. It calculates the stretching factor. So then in principal component analysis, what you do is you sort all these numbers and you get the top, I don't know, 10th or something. And so you find the largest stretching in the dimensions. Okay, so anyway, so the whole point of this is Remember theta is equal to x transpose x inverse x transpose y, right? The problem is we can't always compute this, right? We can't always. Because either point 1, the matrix is not going to be square, but all of this is always square, right? Normally the determinant of x transpose x is sometimes 0, right? And also because you can't invert, right? Because the columns are multiples of each other, right? 1, 2, 1, 2, 2, 4, right? You can't do this. 3, 8. No. Oops, 3, 6. Right? You can't invert this because the columns are multiples of each other. That's just that unfortunately that sometimes happens. So with these problems, actually this always happens, I have to say. Well, not always. 50% of the time you actually have this problem. I'm not joking. Because you know when you do algorithms and when you do the inverse, you sometimes have numerical remember, like a computer only has some sort of precision level, right? You can only, computer only has like 0.0000, 32 zeros and 1, right? Anywhere smaller than that, the computer will just round it off to that, right? So in fact, sometimes when you compute the inverse with a computer, you will have problems where the inverse can't be computed. Because it's just computer. Like the computer can't take small decimals or large numbers. Unfortunately, we can do it by hand, have fun, but a computer can't, right? So that's why this problem exists. But what's this? X transpose X inverse X transpose. That's just X pseudo inverse times by Y. So in fact, remember I said this was the original formula for linear regression, right? So I think many people probably had a question before, I think. I also had the problem. Can't you just take the inverse of X and then, right? Can't you just times the inverse of here? And then this goes to identity, and then just that? Can't you just do that? Right? Do you guys know what I just did? If you take the inverse of x, you times it on, it's just identity, you just get that, right? But obviously you can't do that. But in fact, with pseudo-inverses, yes you can now, right? This is in fact the pseudo-inverse. It's just a different formula. If you can't take the inverse of this, it's technically that. So now you actually have the formula for linear regression. It's just theta is equal to the pseudo-inverse times by y, which is technically the same thing as saying x inverse y. And the pseudo-inverse is just that, right? In other words, the pseudo-inverse is x transpose x inverse x transpose. Okay? Yeah? So what it means, so the whole point is, if I have x times theta is equal to y, I want to find the thetas. I want to find the numbers, which you times the age plus the height times whatever, gives you happiness, right? You can't just take the inverse of x, right? You can't just do x inverse, right? Remember, x inverse times by x is just the identity matrix, right? You can't just do that. But you can take the pseudo-inverse. The pseudo-inverse times x is actually the identity. And you have pseudo-inverse times by y is just the theta. What's the time? Oh, okay, well, I have like 3 minutes or, I don't know, 2 minutes. Yeah, do you guys get that? So do you understand why we're using singular value decomposition? Why we used eigen decomposition? And why the hell we're using pseudo-inverses? No, kind of? So the whole point is, so the key takeaway is, you want to find linear regression's coefficients. Sometimes you can't find them because of these issues. Like you can't, the determinant is 0, numerical instability because you know the computer has some sort of precision. You can't go over 32, well actually there are like 128 digit long decimals. But anyway, otherwise you can't actually compute the exact inverse. So you have problems. Instead, you use a stable algorithm called singular value decomposition. And now you can compute inverses of everything. So that's the formula you have to remember. The pseudo-inverse is V times sigma invert. Technically, you can just write inverse. If you want. Times U transpose. And you just plug it into the computer and you should get your result. Yeah. So one thing that we were supposed to discuss about was confidence intervals and prediction intervals. Oh wait, actually I'll just talk about this central limit theorem and then I think we'll be done because I don't have time. Probably do that next time. Okay, so do you guys know what the central limit theorem is? Can anyone describe me in one sentence what is the central limit theorem, or the CLT? There's a big confusion about that as well. Yep.
Is it that statistics samples, like the distribution of statistics of a population will tend to be normal?
Correct.
With like,
So the misconception people always have is, the first one is, if you have more data, it should look like a normal distribution. Okay, that's totally incorrect, right? Just look at income distribution. If you have over time, does income distribution look like a normal distribution? Clearly not, right? So the central limit theorem says, if you get more samples of statistics, like what you said, so statistics mean the mean, the median, the mode, also the parameters, right? So it's not really statistics. I think a generalization would be parameters. Any parameter. So the mean is a parameter, the median is a parameter. So what parameters mean? You remember linear regression? X theta is equal to y. These are called parameters. Right? I'm going to, well, not always, okay, but these parameters, on average, if you get more and more data, these parameters, not the x, the parameters, should look like a normal distribution. Right? Some sort of mean, right? Some sort of mean mu, and some sort of variance sigma, right? Or sigma squared, standard deviation. No, I said most.
I thought central limit theorem was just mean.
No, it's also parameters. Otherwise, how do you construct confidence intervals?
No, that's not central limit theorem. That's using maximum likelihood estimation properties of MLE estimators.
No. Oh, wait, I'm not going to write the formula now. No, like the
Yeah, that's not central limit theorem.
No, that is. That's the direct consequence of the central limit theorem. This is your normal distribution, and then this is your standard deviation divided by your. That's the consequence of the central limit theorem. If it satisfies the central limit theorem, then only you can use this formula.
I disagree. We can talk about that.
Okay, we can talk about that later. But anyways, this is what your so what confidence interval means is that so remember I said like if you have some sort of prediction, right? Pretend this is your predictions, right? This is your y prediction. The point is, how do we what's the bound? Like that's the bound, right? How do we actually compute these bounds? And you can use that formula, although not
Maybe we can go next week.
yeah, probably it will come out next week. Yeah, okay. I think that's all then. Thanks. If you have any questions, you can ask me afterwards. Yeah.
Just a point with that, guys. With any learning, you never want to trust one source of information completely. So always question Daniel.
Yep.
Always question Johnny. Look it up on the internet, back it up with alternative sources, and form your own opinion based on all the research you gather and distill.